On the last page, we started to look at electron pairs that were repelling each other and getting space, and we're going to continue that and actually build a whole table. This is going to have all the possible shapes on it. So just to refresh, we had been looking at these electron pairs, and those electrons repel each other. And then anytime we're going to find these shapes that occur when electron pairs repel each other, we want to keep an eye out for the center atoms. And we can highlight those on every molecule here. It's a good first step. Find that center. And then from the center, we can find where those electron groups are, okay? So we had looked here on this Lewis structure. I have 1 electron group, 2 electron groups. And so those 2 groups around the center repel each other. And we said that we get a linear electron geometry with 180 degrees between the 2 groups, all right? And that was this picture. I've just switched it to blue electrons now. We also, on the last page, had looked at this molecule, which has 1, 2, 3 electron groups around it. And I'm just going to put a generic X in the middle of it, but this was the electron arrangement that we saw for that one. Color them in to emphasize them. We said that this was a trigonal planar shape. And sorry for the background noise, we have 120 degrees in that trigonal planar shape, all right? Now, looking at unbonded pairs on this center here, I have 0, everything is bonded. On this molecule, I had 1 unbonded pair, so that was this one right here. And so that meant when I drew the molecular geometry over here, the shape that I can see, once I put the atoms on, I had this bent shape, right? Where I have this lone pair of electrons up here, so it was like a ghost that we were holding space for, okay? And this shape, this molecular geometry was called bent. And again, I have about 120 degrees between these atoms here, okay? So far I have these 2 electron arrangements. I want to give you another possibility for this electron arrangement right here. So look at this boron surrounded by 3 fluorines. So it's got 1, 2, 3 electron groups around it, okay? Which means those 3 electron groups will always give each other as much space as possible. That's going to be this picture here. Over here with the nitrite, and I forgot the brackets here, with the nitrite, when I drew that, all I could see with the atoms was this bent shape, right? But look here, in the boron, I've got 3 fluorines. And so if I look at the shape that I'm going to get for that, I have the boron, and then I used orange for fluorine. And so I can see that this shape is exactly reflected here, right? They're the same shape, same angles. And so I'm going to draw this molecular geometry. It's going to be boron, fluorine, fluorine, fluorine in a, again, flat triangle, which means that this molecular geometry is called trigonal planar, and it's got 120 degree angles, all right? And that was when I had no ghosts, no unbonded pairs in the middle. If I have no unbonded pairs, then my electron geometry is going to be exactly the same as my molecular geometry, all right? And I forgot to write it up here, but this is that same scenario. I had 2 electron groups on the center, and then no unbonded pairs, and so my molecular geometry is exactly the same. It's linear with 180 degrees, all right? So now that we've looked at this, 2 groups get a lot of space, 3 groups get a little bit less. I'm going to give you our final electron geometry, and I've changed it to green here. And you can see that, just like home, 2 people, you got a lot of space. 3 people, getting a little more crowded. Add 4, and now things are getting a little bit crazier, all right? Looks kind of cool. It's more fun, but it's also a little more crowded, okay? So this geometry is going to work for all of these molecules here. So check out this carbon. Carbon's got 1, 2, 3, 4 electron groups around it. This nitrogen has 3 atoms and then 1 lone pair, still adds up to 4 electron groups. And this water, which we've seen before, has 2 lone pairs and 2 atoms, so it also has 4 electron groups. You see how this is structured in order on purpose? So how do I draw this and what do I name this? Okay, it's a little bit hard to see, maybe a lot hard to see here. Let me give you a different picture of it, the little bit different model. If instead of the big kind of electron groups, I put sticks on it, maybe you can see that this would be kind of a pyramid shape. Here's the top of the pyramid and here's the base down here. The way that we draw this is going to be the same in every single chemistry lab class around the whole world. Okay, so I'm going to take center and I'm going to draw a bond up. That's this bond here. And then I'm going to draw this bond here, just straight out. And you could imagine that there's a plane that both of those go into, sheet of paper. All right. Then notice that this stick is sticking out at you, right? It's a little below the carbon, but it's sticking out at you. And so the way we draw that is with what we call a wedge. The wedge says, hey, it's popping out at you. And then this one is going back into the paper or down into the plane. And so we draw that again a little below the carbon, but with a dash. All right. And this is how we draw this shape every single time. This is a little bit easier than this, but you can see this is kind of the same, straight up, over, popping out at you, and then going back into the page. I could color this with my green regions to say, hey, these are 4 electron regions that all want to be as far from each other as possible. And the name of this shape, like I said, it's kind of like a pyramid. This is called tetrahedral. Make sure you either build this if you have a model kit or build it online or both, and so you can kind of play around with it. So this is tetrahedral, and what do you think is going to happen with my bond angle? It's going to decrease, right? The more groups I have, the less space they get. 109.5 degrees is what these angles would measure out to. So if I could measure this angle all the way around, every single angle would be 109.5 degrees. So let's take each of these individually then, kind of like we did here, and see what happens. So on this molecule, I start with my electrons, and every single one of those gets an atom. So when every single one of those gets an atom, this is what it looks like. See that? So I have atom, atom, atom straight up, and atom here. So if I draw that, I'm going to keep this exact same method. I'm going to put a carbon in the middle, H, H, down a little to an H, and down a little to an H, popping out at you, going back into the board. If every single spot is taken, then remember these geometries are exactly the same. So this would be a tetrahedral molecular geometry with 109.5 degrees of space for every atom. All right, so that was the first one. Now, what happens if I take this exact molecule and instead one of these is a lone pair? So now I can't see an atom there anymore, but I still have this ghost that wants space, right? And so when I go to draw that, it's hard again to see on the paper, but when I go to draw that, I'm just going to mimic this exactly. So this has turned into a ghost of electrons, wedge, dash, and don't forget there's this ghost of electrons here that wants space. And so I get a slightly different shape. It's kind of like the bottom of my pyramid, right? There's still a bit of an angle. I don't know if you can see it, but it's still a bit of an angle. It's not flat. This was trigonal planar where it lays on the table, but this is a bit of a pyramid. It's up above the plane of the paper. And so the name of this molecular geometry is trigonal, because you can still see that triangle, but I call it trigonal pyramidal or trigonal pyramidal. And again, the bond angle hasn't changed because I still have 4 groups. So it's going to be right around 109.5 degrees. All right, that's ammonia, if you have ammonia around your house to clean with. Finally is water, and we've actually seen water before, right? We know it has that bent shape, so I'm still working off this tetrahedral electron set, but now for water, watch what happens. Water has 2 lone pairs, so that would be 2 of these sticks with nothing on them. And if I can look at what happens to the shape, now that I understand that there's 2 electron pairs here that are helping repel, now I can understand why water has this bent shape and it can't just go up linear like this, because if it was linear, now I have a crowd here, right? So because I know that there's those kind of invisible electron pairs, I can understand the bend in a water molecule. So when I come over here to draw my water molecule, it's got those two lone pairs. Here I had one and here I had none. Once I have two, I can literally draw this flat. Let's just keep it easy. So I don't need wedges and dashes anymore. I call this shape bent. And again, it's about 109.5 degrees. It's actually a little bit less than that, but look how it just lays bent here. And this is, if I was to look at where my electrons are, this is here, right? And then there's the two unpaired electrons up on top that need some space also. I just can't see them when I go look at the molecule geometry. So that is all of your geometries. On the next several pages, you've got space for a lot of practice. Actually on this page, you've got a book version of what we just made here, same exact thing. And then you've got a lot of practice. We'll be doing this in lab and also in lecture. So you can try a couple on your own and then come to class ready to ask questions and work on more.